Hi guys, I'm Anush Ramarajan K of S7ECEA and I'm guided by Sumita Joseph, Assistant Professor of ECE Department. So I'm going to discuss about memory technologies for future computers. So let's move on to the topic. So these are the table of contents that I would like to discuss. First we will um, begin with a small introduction. Then we will move on to the history. Then we will discuss about various types of memory. Later we will discuss about its advancements. Then we will see some applications of the memory, and then we will see the memory market. Okay, so what is a memory? Memory is the electronic holding place for data and instructions. So technically speaking, there are two types of memory: volatile memory and a non-volatile memory. So the memories that can retain its contents when its power is lost are non-volatile memories, and that that memories which lose its contents when power is lost are volatile memory. So moving to the history of memory. So in 1890, punched cards was introduced by German American inventor Hermann Hollerith. So he devised a method to electrically read the whole stone into punch cards. Later in 1932, magnetic drum was introduced by Getzel Hershey. So this magnetic drum is basically a metallic cylinder coated with magnetic material. Later in 1955, magnetic core memory was introduced by George Devon. So this magnetic core memory utilizes an array of magnetic toroids, where each toroid is capable of storing a bit. Later in 1956, hard disk was introduced by IBM, and later in 1971, floppy disk was introduced by IBM, and later in 1980, compact disk was introduced into the market by Philips and Sony. So till that time, all those memory technologies that was introduced into the market was based on the magnetic encoding. It was only in 1980 that a compact disk was introduced, which used semiconductor laser technologies to store data. Later in 1994, compact flash and zip drive was introduced by iOmega and SanDisk. Later in 1995, DVD was invented by multiple companies like Philips, etc. In 1998, memory stick was introduced by Sony, and then in 2003, Blu-ray disc was introduced by Sony. So the main difference between a Blu-ray disc and a normal disc is that Blu-ray disc uses a much more smaller wavelength light to record data onto the disk. This enables the writing arm to pack the data much more precisely onto the disk. Later in 2005, micro SD card was introduced by SanDisk, and in 2015, 3D Crosspoint was introduced by Intel and Micron together. So even though it is written as 3D X-Point, it is read as 3D Crosspoint. We will discuss about 3D Crosspoint later. In 2019, CF Express card was introduced, and the future of the memory technologies lies in decentralized clouds. So let's discuss about the various types of memories. So these are the types of memories that I look forward to discuss today, and these are flash memory, the 3D Crosspoint, phase change memory, ferroelectric RAM, nano RAM, quantum memory, and memory stir. So flash memory. So a flash memory has millions of charged RAM memory cells that are made up of MOSFETs. As you can see in the figure, a flash memory has an oxide layer between the control gate and the floating gate. So whenever the floating gate is activated, it punches electrons into the oxide layer, which gets trapped inside the oxide layer. So since electrons are trapped inside this oxide layer, it is also called a charge trap memory. So if electrons are present inside the oxide layer, it represents logic 1, and if electrons are absent in the oxide layer, which means there is no charge in the oxide layer, it represents a logic 0. So let's discuss about the advancement in flash memory, improving input-output performance via address remapping in non-volatile interface. So an address remapping scheme was proposed which transforms random access patterns into sequential access patterns. So the system first identifies if it is a write or read request that is given to the device drivers. If it is a write request, the linear block address of the request is transformed into a sequential block address, and then it is inserted into the address remapping table. So if it is a read request, the transformed linear block address that is already existing in the address remapping table is used to access data. So this is the proposed block diagram of the address remapping scheme. So as you can see, we cannot make any kind of adjustments in the application layer or file system layer or block layer. So the address remapping scheme is introduced with the device drivers. So as I've already said, it first identifies whether it is a write request or read request. If it is a write request, the address remapping is performed and a search is performed on the remapping tables if the address is already present inside the table. If the address is present inside the table, it is removed and it is updated with the newly transformed address, and then the write request is submitted to the queue. And if it is a read request, the transformed linear block address is searched among the remapping tables, and if the address is found, the read request is submitted to the submission queue, and then the data is fetched from the memory. Moving on to the 3D cross-point structure. So the figure shows the 3D cross-point structure memory. So that blue perpendicular lines are the selectors, and the figure shows the 3D cross-point structure. Perpendicular wires connect submicroscopic columns, and the white and the yellow and green structure together form a single memory cells, and they are interconnected with the selectors, which are represented by the blue lines. So the main advantage of this memory cell is that it doesn't require a transistor to read or write a bit into the cell. So it is also a type of non-volatile memory which can be utilized as for storage as well as can be used as a RAM. So when voltage is applied to the top and bottom selector, it causes the cell to be read or written. The individual cells can be accessed by selecting the top and bottom wire. So moving on to the advancement in 3D crosspoint. The first figure shows the conventional 60 RAM. So it consists of a simple SRAM portion and a non-volatile port directly connecting two ferroelectric capacitors. So these ferroelectric capacitors perform the activity of non-volatility, and the second figure shows a similar kind of RAM. The only difference is that two more capacitors are incorporated into the circuit. So as two more of these capacitors are introduced, it requires one more select line to access the capacitors. That select line is represented by PL2, and in figure 3 it shows an array of such ferroelectric capacitors incorporated into the structure. So if more and more capacitors are incorporated into the cells, incorporated into a single RAM cell, it's capable of forming a 3D cross-point structure. So that is represented by the third figure. So moving on to phase change memory. Phase change memory is a key enabling technology for non-volatile data storage at nanometer scale. So this phase change memory data is stored by using the electrical resistance contract between a high conductive crystalline phase and a low conductive amorphous state. As you can see in the figure, that pink portion, that is the amorphous layer. So the electrical resistance of this material is used to store the data. The phase change material can be switched from a low to high conductive state and vice versa through applying electrical current pulses. So if a low current pulse is applied to the material, it performs a set operation. Means the amorphous material is converted into a crystalline material, which makes it much conducting. And if a short high current pulse is applied, the crystalline material that is already present inside the memory is converted into an uh, amorphous state, which has high resistance. Hence, it doesn't conduct any electricity. That represents zero logic. So, if a high resistance state can represent a logical zero, while a low resistance state can represent a logic one. A low current pulse set is applied to bring the PCM device to low resistance crystalline state. A short high current pulse is applied to bring the PCM device to the high resistance amorphous state. I have already discussed the set and reset operation. Moving on to the advancement in PCM, the phase change memory cell with reconfigured electrode for lower reset voltage. This proposed structure consists of one selector and one resistor combination with a reconfigured middle electrode that wraps around the phase change material. So this phase change material is made up of germanium arsenic tellurium component. This phase change memory cell is currently configured in a multi-level hierarchy, and one resistance part is structurally reconfigured here. The middle electrode is enwrapped. The structure of the electrode tends to redistribute the potential drop, the current density, and the temperature gradient across the 1R region. As the reset voltage and leakage current decreases, the power consumption decreases. As a result, the varied temperature distribution directly affects the phase change behavior. So this system mainly for reducing the reset voltage and thus the leakage current of the phase change material. So as the phase change material is reconfigured here, it subsequently reduces the reset voltage and thus the leakage current. So the capping electrode is also configured here. Mainly, four of reaching reset voltage and leakage current was working on the stage element. The middle electrode is also configured with the capping and wrapping around the resistor region. By doing so, the set and reset voltage decreases. Thus, the power consumption decreases. Hence, the leakage current also decreases. And the recrystallization time is much reduced to 20 nanoseconds. And that's it. Moving on to NanoRAM. So NanoRAM is a type of non-volatile random access memory based on mechanical position of carbon nanotubes deposited on a chip-like substrate. So if the carbon nanotubes are in contact, it represents a logic 1, and if the carbon nanotubes are apart, it represents a logic 0 state, which means it has high resistance state. So the conduction of electricity is not possible. To switch the NRAM between the state, a small voltage greater than read voltage is applied between the top and bottom electrodes. So quantum memory. So unlike ordinary memory, quantum memory uses qubits to store data. So quantum memory stores information as qubits, not as binary zeros or ones. So these qubits hold useful computational informations. So these qubits are quantum mechanical analogs of um, binary bits. Moving to the advancement in quantum memory. So this is the proposed figure of the quantum random access memory. The proposed quantum random access memory can implement qubit-based quantum computers. So this is used to write classical as well as quantum data, and it has very high storage. So the proposed architecture can access arbitrary location. As you can see in the figure, the qubit A represents address register, which is used to address the locations of qubit D. And the D stores variable, so qubit A determines locations of other variables which are uh, given to the processor by the processing unit. The size of qubit A is n, and the size of qubit D is m. The other qubit qy is the n qubits of bus register qy are used to carry address of the variable. The m qubits are used to carry the value in the variable to specific location in QRAM, and r qubit is used to distinguish between reading and writing processes. The correlation between the cell and address occurs via the entanglement when the arbitrary process is performed. The write or the read operation is determined depending upon the qubit r. If r is 1, it allows the RAM to read the contents, and if r qubit is 0, it means it is going to write the contents into the RAM. Moving on to memristor technology. So memristor is one of the best types of for implementing RAM. So memristor is a combination of memory and register. So it is also a two-terminal device based on a resistance switching mechanism. So unlike the already existing memory has a serial access scheme. So it has some drawbacks like a huge delay. So in order to avoid that, a parallel access scheme was proposed. So coming to the advancements. So parallel access scheme was introduced to improve the speed of the memory. So this is a single cell that is used inside that parallel access scheme. The word line controls the gate terminal of the transistor, and the source terminal of the transistor is connected to bit line, and the negative terminal of the memristor is connected to bit line bar, and the positive terminal of the memristor is connected to the drain terminal. So this is the parallel access scheme and the serial access scheme. So as you can see, there is a large number of input-output circuit in the serial access scheme, but there is only a single input-output circuit in the serial access scheme. So instead, a single multiplexer is used. So it requires more number of transistors to be used in the parallel access scheme, while a less number of transistors are required to implement serial access scheme. So the bulk amount of hardware are reduced in the serial access scheme, and thus it becomes much more faster. And these are some of the applications of memory. And the DDR4 RAM is used for personal computing and gaming, and LPDDR RAM is used for mobile devices and other simple but complex computing devices. And SD-RAMs are used for artificial intelligence and machine learning, since it requires much more algorithms and steps to be implemented much faster. And DRAM and SRAMs are much more commonly used in Internet of Things uh, like ESP32 or similar boards. And MRAMs are used in automotive, medical devices, and aerospace and other defenses. So this is the memory pie chart of memory market in the period of 2022 to 2024. As you can see, in 2022, the memory market has run over to $144 billion, and in 2023, it has reduced by 41% and has decreased to about $80 billion. And it is proposed that the memory market can increase to increase by 55% to about $122 billion by 2024, and the statistics state that by 2025 the memory market can cross over $200 billion. So let me conclude for what I've discussed today. So we've seen various types of memories and its advancements, and then later we discuss about the memory market. So these emerging memory technologies offer a range of advantages that can revolutionize various industries and applications. So these are the references that I used.